Thank you all very much. I want to welcome everybody to this webinar from the American Nuclear Society's Risk-Informed, Performance-Based Principles and Policy Committee. My name is Prasad Kadambi, and I am chair of RP3C, as this committee is called.
I'm Rose, urgent care Southwest Medical.
Let's see. Okay, the purpose of RP3C is to help modernize ANS standards. Modernization has come to mean that risk-informed, performance-based methods are employed to overcome the difficulties that we all know about from purely deterministic and prescriptive methods. We have been calling these methods RIPV approaches. The Nuclear Energy Innovation and Modernization Act specifically talks about RIPV methods. There's a lot of guidance available on RIPV approaches, but most people have not had reason to become familiar with the guidance because the conventional approaches still dominate most things that we do, including standards development. RP3C initiated these community of practice webinars on RIPV to enable practitioners of RIPV approaches to share their knowledge and experience. Today we will be hearing from Ralph Hill, who has been very active with ASME for a long time. And he's going to talk about something that is very new, and you know, I look forward to hearing from Ralph. Ralph, please take it away.
All right, thank you, Prasad, and welcome everyone. First of all, I just hate to start with a copyright disclaimer, but it's important that you understand that the key thing is any remarks I'm making, I'm speaking as an individual, and I'm not speaking on behalf of ASME. Since I'm not as well known in the community, ANS community, as I am within ASME, I thought I'd give a brief background. As you can see here, I've been active on codes and standards for 40 years with ASME, primarily in the nuclear area. I received a number of awards. I'm past chair of Section 3 for nuclear construction, nuclear facility components. And although I have been retired for about 5 years now, I've continued in my codes and standards activities. I tell everyone I gave up and retired from my paying job, but not from my volunteer job. And currently I'm on the ASME Council on Standards and Certification. I'm also on the board on nuclear codes and standards. And most importantly to me, where my heart is, on champion and chair of the new Standards Committee on Plant Systems Design, which is the subject of this presentation. I'm also, so you know what I look like, and then ANS, I'm a member of working group on ANS 30.1 for a couple of years now, and 30.2 is being reconstituted, so I'm supporting that. And of course, I'm a member of RP3C. Today, let me start off. I've been a champion of risk-informed lifecycle design concepts for over 20 years. And considering the many initiatives today and in the recent times to support advanced plants, I think the time to implement risk-informed lifecycle design concepts is now. And initiatives that we're talking about include things that you're familiar with: the licensing modernization project, the new NRC Part 53 that's just started out, as well as the ANS and ASME initiatives to provide standards that are more relevant to the unique and varied safety cases for the advanced plant designs. In addition to providing an overview and status, as you see here on the topics of the ASME Plant Systems Design Standard, this presentation is also my attempt to put some pieces together to provide a concept for risk-informed lifecycle design that also incorporates the risk-informed performance-based principles that Prasad has introduced. So, first of all, we're going to do an example of where risk-informed design actually has been performed. This was done, believe it or not, 13 years ago. We used a Monte Carlo simulation tool called GoldSim for a very simple fluid injection system where the model and assumptions were out of the blue. They were good engineering estimates, but they're not relevant to any actual design parameters. And it's for demonstration of the technique only. It shows how the system can be analyzed in a risk-informed approach. It's applicable to all types of systems of varying levels of complexity. And it can be applied at multiple levels ranging from entire system to a subsystem, down to the level where requirements are actually defined. So the top level requirement for this system, it's a fluid injection system, and you see the schematic here, is able to inject 200 gallons per minute with a mean reliability greater than 95%. On the left, you'll see the charging tanks with pumps and valves feeding into the injection tanks of 4 trains, with injection pumps and injection valves then feeding into the plant. So there's a number of general assumptions on component failure, modeled simplistically with Poisson distributions. The initial failure rate depends on component quality. Failure rate increases exponentially with time following any maintenance or repair. Doubling time depends upon the component quality. We have pump's fallow rate that depends upon component quality again. Maintenance occurs at selected interval unless inspection reveals failure rate is above the target level. Inspection occurs at sub-intervals or maintenance intervals. And when inspection occurs, there's a probability that it misses the fact that failure frequency is too high. So not totally unrealistic. In regards to the injection system itself, the assumptions, any 2 lines can satisfy the requirement. The tanks drain due to demand and are filled from the charging system. System is offline if more than 2 injection lines are unavailable. If the injection line is unavailable, if either a valve or pump is out of service, a pump is sufficiently fouled, or the volume of a tank becomes too low. Then assumptions on the charging system. If any component is out of service, injection tanks cannot be filled. They can be out of service due to maintenance or repair. The charging pumps are also out of service if sufficiently fouled. I had to find a place to stick the citation for the paper where we published this. You can see we did it at the International Conference on Nuclear Engineering, our ICON 11 back in Tokyo in 2003. So, but the model is still as valid today as it was then. So this is table 1. If you see at the bottom, it's a case study input. On the left-hand side, you'll see the components of the system, injection valves, inspection pumps, etc. The next column, you can see their model is good, very good or excellent. Their maintenance frequency, it varies from days of 100, 250 to 500 days. Inspection duration, we have functions, frequencies, different frequencies for each component. In the center, you'll see we can also model capital cost information. If we were doing this at a trade study and we want to model radioactive exposure, LAR considerations, we could also include LAR information as part of the decision-making tool. And then on the third column, you see the component reliability information. I guess I could use my mouse a little bit here. For initial failure rates, the doubling time, and the target frequency that forces inspection. And then we have pump discharge information over in the right-hand column, a number of additional assumptions at the bottom. So what about the results? So the results are shown here. Again, at the top 3 rows, you see all component qualities were excellent, different maintenance frequencies, different inspection frequencies. Injection tank volume was static for all 3. Input rate the same. Now you see your system reliability results. For the first row with the inspection frequency of 50, we had 95.3 mean. Then we had 94.7 mean for inspection frequency of 250 days and a frequency of 25 days and 95%, 95.2% reliability. So the key here is that the choice of component quality and injection tank design parameters results in a system reliability that meets the performance regardless of the maintenance inspection intervals. Remember, our initial performance criteria was 95%. However, there's still an approximate 50% chance of the system reliability being greater than 95%. An analysis of the results indicates that overall reliability is controlled by the reliability of the injection tank. And then the following cases, which we won't go into here, consider larger injection tank. And you can see here, you get larger mean system reliability results with larger tanks. So I think this very well illustrates the value of a tool like this in evaluating a system from a design standpoint, from a trade study standpoint, invaluable, and it also provides insights into the reliability of a system. So in summary, in this area, what do the results say? Excellent components for maintenance and inspection. Large injection tank can meet the goal with ample margin. But the case we looked at, the system would be over-designed. So it could have a significant cost associated with it that we might be able to save costs by looking more critically and refining the design. Several options exist that meet the target goal. We need to consider desired level of risk tolerance. Is the 95% acceptable? How do costs play into the decision? Larger capital, lower O&M, what if we wanted to bring in ALARA? Decisions made to determine which options are advanced to the next phase. Subsystem requirements can be defined and subsystem models can be further refined and optimized. So with that, I'll pause and take a couple Q&As before we move on.
Hey, Ralph, and checking the Q&A. I do not have any questions at this moment.
All right, perfect.
Yeah, why don't you go ahead, Ralph?
I will do that. So the next section we're going to look at is overview and status of the ASME Plant Systems Design Standard. So the problem that we're addressing with the ASME is addressing with this standard is that new plants and facilities with potential for significant environmental safety and health hazards to the worker and the public may not be built here in the US unless we can bring down the cost of license, design, and construct, but still ensuring safety of the health of the worker, the public, and the environment. And when we talk here about hazardous plants, for the purposes of our standard, we're talking about plants and facilities that include nuclear, fossil power, chemical, petrochemical, compressed liquefied natural gas, hazardous waste, and perhaps others. So we're tech neutral from the standpoint, we're not just nuclear. And then of course, obviously we're tech neutral within the nuclear community also. So solution is again, tech neutral standard that provides a framework, including requirements and guidance for design organizations to do three things: conduct plant process analysis in the early stages of plant design, that advance as the design matures, and provide structure to the initial development of a quantitative risk assessment. Secondly, incorporate systems engineering design processes, practices, and tools with traditional architect engineer design processes, practice, and tools. Thirdly, incorporate risk-informed probabilistic design methodologies with traditional deterministic design methods using reliability and availability targets. And integrating these into a design organization's existing design processes and procedures. We're not telling him to throw out everything he's got. We're telling him to bring in some improvements to bring down potential costs. We all know it's the costs in the final or detailed design stage, the errors we catch there, those we catch in construction or in startup and test or commissioning, those are the ones that cost us the most. So the focus of this standard is to bring down the potential for those errors to occur and thereby reduce the cost of construction. Here we see influence diagram that shows the relationship between the three technical areas in the standard in relationship to plant design. Remember, we said those technical areas were early hazards analysis leading to quantitative risk analysis, systems engineering, and probabilistic design. So here you see systems engineering encompasses the entire process from pre-conceptual design through final design and support to construction, startup, and decommissioning. That's the design, field change requests, things like that, feedback in, and we have to handle those. The plant hazard analysis provides qualitative plant risk evaluations during early stages of design, supporting the quantitative PRA or QRA or PSA analysis in later stages of design. And the probabilistic design methods has the greatest applicability in the later stages of design, probably really in more in final or detailed design. And all three technical areas support field changes during construction, startup, and decommissioning. So the objectives are safer and more efficient designs and design alternatives with quantified safety levels. Now, in the past, or with current design techniques, ASME code, et cetera, we can't quantify the risk of one system design versus another, or the risk of the plant. But using the type of Monte Carlo simulation we showed at the beginning of this presentation, and we can start to do that. More effective requirements management. In my experience, over 40 plus years in the industry, that's an area where typical architect engineer processes have fallen down. These would include assumptions, what we call TBDs, to be determined, and TBVs. So you have a high level specification with a piece of information that is either an assumption or we're not sure about it or needs to be verified. Tracking those things through the myriad hierarchy of documents we developed during design has sometimes been very difficult to do. Covering the entire life cycle of a plant design: construction, operation, decontamination, and decommissioning. And be system-based versus component-based, and inclusive of multiple disciplines: mechanical, electrical, I&C, et cetera. Typically, ASME standards have not been system-based, they've been component-based. Now, there are a number of related initiatives, of which what you see on your screen here is just a few to what we're doing with the Plant Systems Design Standard. We already mentioned Licensing Modernization Project, NEI 1804, Reg I 1233, Part 53, the risk informed safety categorization process of Part 69. ANS has a number of standards, including 30.1 and 30.2. The EPRI body of knowledges, which talks about evolving through hazard analyses, evolving to support as building blocks for PRAs. The ASME Board on Pressure Vessel Technical Technology Codes and Standards, so that's Section 1, Section 8, et cetera, has a task group on risk-based design that's identifying areas and recommendations for Section 1, Section 8 to incorporate risk-based design into their standards at some point in the future. And then Section 11 of the ASME Code for in-service inspection, Division 2, which is fairly new, a year or so old, as the RIM program, or requirements for reliability and integrity management for nuclear power plants, that also is risk informed. Now, relative to the ANS, they're developing a series of standards to support new plant designs. This graphic shows the three top level standards, addressing risk and performance objectives, categorization of structures, systems, and components, and risk-informed decision-making. They provide requirements and guidance to the next tier of standards that address reactor-specific designs: fluoride, salt-cooled, liquid molten salt, helium-cooled, et cetera. At the very bottom of the graphic down here, you'll see reference to other standards, including cross-cutting topics. This is where the Plant Systems Design Standard integrates into the ANSA standards development planning is shown on this figure. An architect engineering firm would use the applicable ANS standards in conjunction with the Plant System Design Standard. Now, I do recognize this slide. I got it from Mark Lynn about 18 months ago as part of ANS 30.1, and it's old and probably not current, but I think the message here is very relevant. The focus of our first year with the Plant System Design Standard has been detailed planning. By the way, we got approved as a standards committee in July of 2019. So we're a little over a year old. So our first year was detailed planning of the content. So we spent a whole year planning what the content was going to be around those three technical areas, and how we did brainstorming sessions, roadmap for each of the three technical areas. The roadmaps and process flow diagrams were used to develop work breakdown structured data sheets with descriptions of each part of the standard and identification of inputs from and outputs to other parts of the standard. So we did all this detailed planning. The block flow diagrams and N-square diagrams, we're using those to integrate activities within each technical area and to integrate the technical areas together. In the past months, we have been importing this information into a InnoSlate, which is a model-based systems engineering cloud-based software tool to plan and organize the contents. I probably went a little bit too fast. Progress to date. Okay, so what we are essentially complete with planning each of the 3 technical areas and doing final edits to the planning information we imported into InnoSlate. Once a complete integration of the 3 technical areas, we can complete our baseline project schedule. And then we can estimate completion of the initial issue of the standard and measure progress. We're targeted to have an integrated roadmap and plan completed early next month. Another key feature of having an integrated schedule is we can identify where what I call the long poles in the tent are. Those sections of the standard that are going to take the longest to develop, and critical path, if you would, if you're a scheduling guy, and then go out and get some outside resources to help bring in the development time for the whole standard. Now, in parallel with completion of the integration scheduling activities, excuse me while I take a sip of water. So in parallel with completion of these activities, we've drafted introductory sections of part 1 of the standard, including sections on tailoring use of the standard, safety goals, taxonomy and boundaries, technical baseline descriptions. We also have sections addressing the applicability of the standard to areas such as regulatory conformance, licensing considerations, and industrial hazards, occupational health, and safety risk. We also have a section I'll show you a little later looking at RIPB and how the standard relates to that. A few months ago, volunteers began writing the first sections of part 2. Results are being used to provide guidance to other working groups. As of today's presentation, initial drafts have begun in all 3 technical areas. So we're beyond just our planning stages, we're actually starting to write in parallel with finalizing an integrated schedule. Let's see. I got out of sync here a little bit. Okay, so again, back to InnoSlate, the software tool that we're using. It enables us to better identify the interrelationships between different parts of our standard, as we mentioned. And what you're seeing here is an InnoSlate generated action diagram. Here, where you see the acronym SIP, it stands for Site Infrastructure Plant, which is the highest level we use in our taxonomy for the standard. Plant level of requirement, excuse me, the green shaded parallelograms represent inputs to or outputs from the blue shaded activity block. So this is actually a set part of the standard that we will be writing and started writing in the area of hazards analysis and evaluation. In the early conceptual design development stage, after we receive the contract technical requirements, et cetera, we identify the hazards and causes, develop the event sequences, evaluate the event frequencies, the consequences. We identify barrier functions to either prevent or mitigate those consequences. We characterize those risks, and obviously there's do loops in this process. And then we validate those risks. The output from these activities feeds into the functional baseline, which is then the basis for the next stage of design development, which you can think of as preliminary design or development of the allocated baseline, if you are familiar with that terminology. So this is typically the way we planned our work and how we'll be writing sections around each one of these. And you can see there, each of these is decomposed into more detail also, and written about, covered in the descriptions and material in the standard. And I already covered this. So we'll now talk a little bit about the structure and of the standard, looking at the process overview, our taxonomy and baselines, our hierarchy of documents and products, A little bit more on use of InnoSlate. I want to show you an example of the Part 2 content and talk about what we show you the section in Part 1 that discusses risk-informed performance-based design. As we indicated earlier, systems engineering principles and processes are a key element of our standard. This graphic shows many systems engineering principles being included in the standard in this stylized V diagram as applied to a typical architect, engineering, or nuclear plant project. Starting from the various requirement sources on the left, the systems engineering analysis, we call it engine, if you would, works to understand and derive requirements to determine the required functionality, establish facility and system architectures, and to specify required verifications and validations. This engine develops baselines in a top-down manner, as is common in system development. The requirements established within each baseline provide the basis for development of the next level of baseline requirements. These baselines, if we're looking at the V, they can come down the left as you go back up the right side. They establish the means to verify and validate the requirements for components and systems, and ultimately at the very top for the facility or the plant itself. Now, all of this work is underpinned by good requirements management and configuration control. And the standard is not going to talk about these programs. It does talk about the fact that they are necessary for a successful project. But as if with any standard or any product we try to produce, we have to put boundaries around it. And these are not included in the content for the boundaries of our standard. Now, although the systems engineering process graph, it might look familiar to you applying systems engineering to traditional systems, we're using a little different taxonomy. We found it necessary to develop this taxonomy because we're technology neutral. We're going across petrochemical, nuclear, pharmaceutical, et cetera. So they all have different terminologies and taxonomies. So this is what we're using for this standard to cover a whole range of hazardous type plants. In this view, we can see the site is the highest level system. It's composed of a plant, could be one or more, and a site infrastructure. Below that, the taxonomy looks familiar with, looking on the right-hand side, you see identification systems, subsystems, components, and the like. In addition, you'll see structures has a leg of its own on the right-hand side because they're specified differently from the system. This graphic also shows which level of the taxonomy is the focus of each baseline. Defining, specifying, and architecting the site, infrastructure, and plant levels are the focus of the functional baseline. So you'll see they're shaded in dark black. The system structures and site grading are the focus of the allocated baseline, excuse me, sensitive mouse there, which is outlined in black. And specification and design of items that are fabricated or constructed are the output of the product baseline, which is not shaded. Some of examples of these are included in the slide. Please, oh, I went up one more. My finger is too fast for me. This slide shows the development, level of development that is typically expected as a result of each project stage. I'm an old-time engineer. I think a conceptual, preliminary, and final design could be detailed design. Some people use that terminology. And then, you know, DOE has brought in the concept of baselines, and that's across the top, your functional baseline, allocated baseline, and product baseline. I think those are spreading more throughout the industry. But the level of development expected as a result of each project stage is what this diagram demonstrates. And for example, the conceptual design stage will result in an approved functional baseline and a preliminary allocated baseline. The important idea here is that each stage works on its primary baseline goal and the one below it. And by doing the one below it, you ensure that the primary baseline is feasible and stable with lower risk to approving it. Although this chart is presented as if these projects perform like a waterfall, that's far from reality. Often it is true that a project is in all stages of design, while it's also in the procurement and construction stages. Usually the main process systems will be heading through the life cycle ahead of the utility system. Site work will be begun very early in a project, often while systems are in preliminary design. Each project can vary widely from one another, depending on the client and how they wish to structure their project life cycles. Please don't try to read this chart. We're using a model-based systems engineering tool, as we said before, to help write the standard. We found it necessary, we found it necessary when trying to get several committees and their members on the same page. Work needs to be transparent and current. The process of trying to share files via email or share drives wasn't very effective for configuration control. So MS Office tools are just not up to the task either. So we're using this model-based systems engineering tool to do the following: develop the functional diagrams that represent the project processes that will be addressed in the standard, show the interrelationship amongst these among these processes and associated document sections, and collaborate with all the authors, regardless of where they are on the globe or what time zone they might live in. This making all the information transparent to all the authors, and providing a standard set of terms, taxonomy, and way of representing data. And then we're actually going to write the sections of the tool. Our initial sections, we're writing those in Word and importing them into the tool. But as our working groups get more familiar and we get settled on our format and the types of content and guidance for each section, so we have it written as if one person wrote the whole standard, then we'll start writing in the tool itself. This is an example from part 2 of the standard. Each activity has 3 elements: descriptive and informational text, which as you see here. No, should, shalls, remains. This is descriptive and information. Then we have the action diagram, and below that, we have the table containing the requirements related to performing the activity. So all requirements in our standard will be in tables. So a user doesn't have to hunt through and look for shall, shoulds, and mays, etc. They'll all be in tabular form. Also makes it easier for volunteer and the writer author and to ensure everything is integrating together. So section 113 of the standard describes what, why, and how risk-informed, performance-based, and risk-informed and performance-based design approaches are applicable and used in the standard. Prasad Katami and I are the authors of this section. Prasad doing the bulk of the work, and I thank him for that. We obviously don't have time to go into this, but it's available for those who may be interested. We can cut and paste and share this with RP3C committee members and others. So that's a summary of the overview and status of the Plant Systems Design Standard. Well, again, we'll devote about 5 to 10 minutes now for Q&A. I think we're doing okay time-wise.
Ralph, yes, you have accumulated quite a few questions now, so they saved them all. I'm going to go ahead and start with the first question, and it's from an anonymous attendee. The question is there any consideration relative to the model to consider condition-based maintenance and inspection versus time-based?
Yes, we intend to cover all the entities. Right now, our intention is, and we're looking for volunteers and input to help us, is we will have sections that describe the importance of the entities and identify where they are brought into design. The systems engineering integration portion of the standard will focus on that. But one of the things that we recognize we need to do a better job in design to ensure we bring down the costs of construction operation is better consideration of operability, maintainability, availability. It's the focus of the standard. We're not even looking just at reliability. We're looking at availability, which includes both reliability and the ability of the plant to achieve its function or its objectives in product throughput and output. So yes, those are very important in the standard.
Thank you. The next question is from Pamela Nelson. She said, do you use an optimization method in the Monte Carlo simulation?
I believe we do, but I'm not an expert on that. But we do have we've been back in touch with the Gold Sim. The software still exists. It has been refined to the extent we can't even run our same simulation anymore with the model we had. But I believe it is, and I can get an answer for that from them.
Very good. I will go ahead to the next question then. And this question is from Don Eggett. But is this standard a high-level document that includes just requirements, or a standard that includes both the requirements and the how-to guidelines?
Good question. Thank you, Don. And I should have addressed that. We're going to provide the what should be done, when it should be done in the sequence of design development and the activities that we showed you in integrating those activities together, and a general description of how, but the specific how to do a load resistance factor design, how to do a PRA. We have toolboxes that we're including as part of the standard in the appendices that provide different techniques and references of how to learn and do those detailed how-tos on each of those techniques. So if you're talking about hazards at HAPRA, you're talking about a hazards analysis, or we provide references to how to do that in our toolboxes.
Thank you. I have another question from an anonymous attendee. Question is, does ASME RAM 1 and RAM 2 complement what is being established within PSD-1, or will PSD-1 replace that?
Did you say RAM? I said RAM 1
Yes.
and RAM 2?
I have a feeling that he meant RIM.
Right.
Oh,
Okay.
RAM? Okay, so that's Section 11, Division 2, Reliability Integrity Management Program. No, I think they're complementary. And we're as we develop our standard, we're looking at both what the Pressure Technology Task Group is doing in regards to recommendations for incorporating risk-informed design into Section 1, Section 8, et cetera, as well as the RIM program, so that we can bring in appropriate aspects to be consistent with them. But we go way beyond the scope of the RIM program.
Very good. Thank you. We have another question from Don Eggett. The question is, why was InstaSlate chosen as the software tool? Is it that well known and currently used in industry applications?
Okay, InstaSlate is well known within the systems engineering community. I don't know if you're familiar with the International Council on Systems Engineering in COSI, but it's well known within that community. It's also a very, very good tool. I've used Doors and Core and other tools in the past. Myself personally, I find InstaSlate to be superior. It's entirely cloud-based, which is a real advantage. I'll get to that. So yes, it is well known, it's well recognized, and even more importantly, the owners of that software have made it available to the committee with no charge.
Very good. Thank you.
One other aside for that, Don, is that I think this is a basis for ASME, and if ANS wanted to embrace a similar approach in the future, to go to cloud-based publishing, where a user can download part of a standard or a standard onto their laptop when they're on the factory floor and say, this is what we're supposed to do. And I'm doing gestures that you can't see. That's where we all need to go, or we're going to become dinosaurs. Excuse me, personal opinion.
Thank you. Our next question is from Clint Miller. Question is, does this initiative need help or input from ASME, Rad Waste Committee, or ANS Waste Committee? Would efforts by these committees to exhume the withdrawn standards interfere with this initiative?
I believe we do. Thinking about our membership, I've got some rad waste background from a codes and standards perspective and from projects I've done with Westinghouse in the past, but we really don't have any expertise on the committee, and we need it. So if there's any interest, please reach out to me. My email is hillr@asme.org.
I also want to remind Mr. Miller that, this is the kind of function that RP3C serves within ANS. And, the Decommissioning and Waste Consensus Committee needs to get involved with RP3C also, because we would be willing to help using some of these methods. So.
Thank you. We have, right now I have 2 more questions. My next question is from Matt Denman. The question is, systems engineering-based design is heavily process-based and slow, e.g. Boeing. SpaceX has really moved into rapid design, build, test iterations instead of long studies between iteration. Doesn't the current RP3C approach lock the nuclear industry into an outdated paradigm that is being shown by the space industry to be longer, more expensive, and less agile than what we could be doing? Why are we standardizing the approach design? Nuclear can still be RIPB without being so devoted to systems engineering and the guiding principle to reactor design.
I think that's actually addressed to Prasad as well as myself. From my
standpoint, I think
Prasad, please let me finish. From my standpoint, I'm a strong advocate of agile engineering, and I've been preaching that for 20 years too. So I'm not familiar with the particular processes you're talking about. I think within systems engineering, we have agile systems engineering also. However, I am please come share with us your information, your insights, your suggestions, anything we can do. And we must do it if nuclear is going to succeed, bring down the cost of construction and operation of these plants.
Yeah, I think in general, there's a lot we can do to move into more advanced methodologies that are coming up. The first thing is we need to open ourselves to all these innovations that are taking place outside. And that, I think, is one of my objectives anyway, in terms of what RP3C can do to help, is open the window out to people who are practicing in other fields. And I can certainly use Matt Denman's help in, getting people acquainted with what he's talking about. So,
thank you. The next question is from Bob Youngblood. Question is, does your development contemplate a possible eventual need to feed into an insurance case of some kind?
Could you repeat that? I didn't catch all of that.
Does your development contemplate a possible eventual need to feed into an assurance case of some kind?
Again, the last part of that I didn't get. Does it contemplate what?
Maybe Bob Youngblood is on the
Yes.
able to talk, perhaps.
Yeah. Yes. So far, what you've talked about is how to make the design best. But I was wondering if you contemplate eventually having to prepare and submit an assurance case, like a safety case, but maybe with a more performance-oriented dimension. So as opposed to like an FSAR or something.
Well, I shall see when the next part of the presentation, Bob, look at that a little bit from that perspective. I would say we support that. Some of this next section of the presentation goes beyond what's in plant systems design, but I think also is relevant to your question.
Yeah, in fact, considering that we are running out of time, Ralph, I'd say jump into the next section and let's cover as much as possible.
All right, I'm game for that. So, this part of the presentation is my attempt to put some pieces together, as I said at the beginning of this today, to provide a concept for risk-informed life cycle design that also incorporates performance-based principles. Now, an example of an injection system was risk-informed and was life cycle, because it included inspection, maintenance, etc. But we're also, so this will talk about, it also incorporates performance-based principles. And again, it builds on the injection system and incorporates areas of systems engineering, risk evaluations, probabilistic design. So it incorporates a little bit of everything that we've talked about so far today. So this is a concept that I put together a few days ago. I actually woke up around 5 o'clock in the morning and it all seemed to come together. So I got up and got on the computer. I think we've all had those moments in our past. So let me walk you through this a little bit. So the plant systems design standard is really aligned in the same fashion that you see here. At the start of the process, you get, sorry. At the start of the process, you get research and development, whatever goes on until the client says, I'm going to build a plant. They establish a contract. Within the contract, you have technical requirements. They're in the basis for your early preconceptual design development. First thing, if you develop your plant functional performance requirements, your hazard identifications, you evaluate those hazards with your risk evaluation. At this level, you're more qualitative than quantitative. This is where I think in this concept, a FC curve fits in, and you identify your key safety functions for the plant. Keep in mind, this is looking technology neutral, not just nuclear, but across different types of other hazardous facilities. All of this then feeds in as form the basis for your functional baseline. That's the basis for the next step of design development. Typically, we call that conceptual design. Again, you design at the system structure level now. At the system level, you're looking at your functional performance requirements, your hazard identification, your risk evaluation, and your target reliabilities. And here's where you establish the safety classification. This is thinking in the context of 30.2 a little bit. And in that perspective, there's a do loop. And all of these have these types of feedback loops. But for the risk evaluation, you identify your safety strategy and safety functions. Those will help you develop, and then you allocate those safety functions and safety classifications that'll be allocated down into your actual product components or hardware, et cetera. So there's a do loop that entails. So again, all these products from your conceptual design development are approved in an allocated baseline. That's the basis for detailed design. In context of an earlier comment, this looks like a waterfall. In reality, in plants, different parts of the plant or system design are in different stages of this at the same time, which makes management even more of an opportunity. So then now in the detailed design development stage, now you're at the product level, your pumps, valves, et cetera, tanks, pressure vessels, the functional performance requirements for those. What's the hazard identification for a pump or a tank? The hazard evaluation, what are the hazards, and then evaluating those hazards. And also, I didn't mention up in here, and it happens down in here also, you're looking at your mitigation strategies, to mitigate the occurrence or mitigate the impact or effects of a unwanted event. And then now down here, getting a product target reliability for that component design. Here we had a system target reliability. Those feed back into the Monte Carlo analysis that we did earlier. You can use that Monte Carlo analysis type of an approach to not only use as a trade-off study tool in doing your design, but also to get an overall sense of the reliability of a system. And why can't that same reliability be used to identify what your safety classification is? So we use target reliabilities or design reliabilities in relationship to safety classification. So we identify for a system has to have a certain target reliability for the plant, and then we can have different product reliabilities that combine to achieve a given system target reliability. It's a different way of looking at safety classification and design than we may have before, at least in my thinking. And that's the concept at an overview level, very rough, very new. I'm looking for input feedback. Am I all wet? Does it make sense? But in regards to input and feedback, well, just at a higher level view, again, looking at what we can do with tools, Again, we established a functional safety classification as a basis for the system structure classifications and as a basis for the product level safety classifications. And then again, there are feedback loops you don't see here. So Kent Welter is a colleague I have a lot of respect for. So after I put this presentation together at 5 o'clock in the morning, I sent it to him, or this concept rather, and asked for his feedback, and we had a good discussion on it. And one of the things that's identified, and he sent off to the RP3C committee members, is this ONR guide, Office of Nuclear Regulation, on categorization of safety functions and classification of structures, systems, and components. And lo and behold, it has a lot of resemblance to the concept that I had come up and shared with Kent, and I'm sharing with you today. 3 slides I'm going to show you quickly. We're not going to go into detail. They want to illustrate that at least one regulator understands and recognizes the relationship between risk-informed performance-based principles, how to implement those principles using good systems engineering practices. Now, again, said we're not going to discuss them. We don't have time, and I'm not that knowledgeable of the guide because I got it from Kent yesterday, I think. But I think the NS 30.2 working group on safety classification for the new plant should include the ONR guide as an input to development of the standard. So I'll share those 3 slides with you briefly. So in the ONR, they have a V diagram. Lo and behold, the things we see here make a lot of sense, are consistent with where we're going with the plant systems design standard. Your project definition, safety function categorization. So you do your functional requirements here first. Then you do your classification based on that breakdown, refining it, your feedback loops, etc. In here, you're also developing architecture as you go down the V, architecture being your pumps, plants, and systems at this level, pumps, plants, hardware down at this level. And then again, as you develop these, you develop your acceptance criteria at the design level, the functional level, as you come back up the V. So they're also looking at operations and decommissioning. I'm going to include those in some fashion. They're also looking at your frequency consequence curves. Where here your high frequency, high consequence are Cat A, and the intermediate is Cat B, and low is Cat C. They're using those types of concepts to develop failure frequencies and probabilities for your safety classes. So failure frequency of this range is class 1, probability of failure on demand. If we need that pump or that train or that system to be online, what's the probability of failure? If we need it to have a very low probability of failure, we make it class 1. Intermediate, class 2. Now we have values, and these values we can use to design to. So back in that Monte Carlo simulation at the beginning of this presentation, we had target reliabilities. Well, that's an inverse of failure, right? So now you can take values like these to establish what those should be for different systems based on the criticality and based on the risk identification, risk evaluations, mitigation strategy, et cetera, we developed during the design process that we showed you the plant systems design is doing. So in summary, we've done an example of a life cycle design using Monte Carlo simulation, risk informed. We've overview and status of the plant systems design. I've shared a concept I have, and I find out that to some extent the UK guide implements and validates the concept that I came up with. And so with that, we'll go to final Q&A and discussion.
Thank you very much, Ralph. I think you covered a lot of ground there. And, you know, the fact is that a lot of this, as you said, is brand new. And, you know, the ANS has a very active working group on, you know, safety classification, and that is ANS 30.2. And, you know, as I say, we just got started. We've had one very active conference call, and we intend to meet regularly every 2 weeks. So, you know, if people are interested, I'd like you to just let us know of your interest. Kent Welter, Don Spellman, and I are sort of taking the lead on this. We are approaching the end of the hour, as it were. I try to keep these things to about 1 hour. I think maybe we can take one question. We have 2 minutes left. So I don't see that there is any question. So
there was one, Saad, there was one, and somehow I knee-jerked and lost it. The question was, did the UK come up independently with their approach, or was it somehow related to this concept? And no, they're totally independent efforts. Theirs has been around a lot longer than mine. They're smarter than I am, I guess.
Well, I did take a look at it. I see a lot of resemblance between what they have proposed and things that we have been talking about for quite a few years, and you know, around ANS and you know, the U.S. nuclear industry. So I think we all learn from each other, and we borrow heavily from everybody else's wisdom, and that's the way it should be. So you know, given that, I would say it's as more important than ever that everybody come forward with what they're doing in their work with risk-informed performance-based methods. And please sign up to have one of these community of practice sessions, and we'll be glad to take you on and put you on the schedule. So with that, again, Ralph, thank you very much. I think this was a very good presentation. We had active participation. And Pat, I guess I'll turn it over to you to finish up.
Okay, thank you all. And I will go ahead and end today's community of practice. If anyone does, however, think of a question after the fact, please go ahead and email me. I'll be happy to forward that to Ralph, and I know he'll respond. Thank you all. You have a great weekend. Bye.
Bye.